All right, AcDec peeps. So, today we're going to enhance your knowledge of counting. See, earlier we talked about an old counting concept. We talked about the concept of, we talked about the multiplication principle. We like that one. Now, I apologize for the people who are currently sitting here watching me do this, because I'm going to be talking to the wall, not to you, but kind of to you, so I'm not going to actually ask you questions. All right, cool. So it's like you get to watch me talk to myself. The multiplication principle was something as simple as I've got 3 pairs of shoes. I've got, I don't know, 4 shirts. How I have only 1 more shirt than I have shoes, I don't know. And I have 3 pairs of pants, because, yeah, why not? And I ask you, if these all match, and you, or on the flip side, maybe you have the style sense of Sean, and you don't care if they go together. No, you're okay, Sean. It does look good. I didn't spell it wrong. I used the incorrect one. And what? So, we have this. What we would do is we would say 3 times 4 times 3, so 9 times 4, 36 outfits total. Now, you have to be careful with the multiplication principle because, remember, in the situation where I'm talking about, say, different drinks from a restaurant, if I've got 3 sizes and 10 types of drinks, and by that I mean, you know, like Coke, root beer, Sprite, iced tea, lemonade, water. I've got 10 types, and I've got an assortment of 30 flavorings. We do have to be careful, because what I can say is that in this, I would say, well, that's 3 times 10 times 31. There are 3 sizes. If I'm ordering a drink, I'm going to get a small, medium, a large. If I don't pick one of those, I'm not going to get a drink. I have 10 types of drink. If I pick something that's not on the list, you're in trouble, I'm sorry. But if I don't want to add a flavor, and by flavors I'm talking about when they add like the cherry, the vanilla, all of that weird stuff that they add at the weird machine. It takes forever because everybody has to line up behind one machine now. And if I'm getting a choice of these 30 flavors, do I have to put a flavor in the drink? I like that I still got an answer even though I wasn't asking the crowd. So that would be 30 times 31, which is some annoyingly large number. What is that? 930? Is that right? Sure. That looks like a good number. And we can say that there are 930 drinks at this particular store. Now, that's all repeat of stuff that we've talked about earlier. That's multiplication principle. That's just a review of that. What I want to talk about now are 2 very, very different things. We've got something called a permutation. And if you were in AcDec before, you should really know the difference between these versus what's called a combination. Both of these are methods in order to count out numbers. These are really, really advanced tools to come up with what we want. However, the big difference between these is that in this, a permutation, order will matter. For instance, if we're talking about a race, well, I care about who's in first, second, and third. If I'm asking about race, like running, not people. Okay, cool. Just figured I could see you all being weird about that. Race, like running, not like people, like, you know, black and Hispanic and white and Pacific Islander and Asian and other assorted ethnicities that races that exist. So we've got race. We've also got races are going to be a situation where that happens. I would just have elected positions. Are going to be an example of a permutation. The reason why order matters there is because the individual, once they're picked, can't be picked again. What? What? Crazy. What else would there be? I don't know. I'm going to come up with more examples in a second. Then there's combinations. I like combinations. Order doesn't matter. Now, combinations are a pain in the butt. Whoa. Why did you change on me? What is that? That was cool. Sorry. Example of things like that is going to be hands of cards. I'm going to come back. I'm going to show an example of that, and some of you are not agreeing with me probably with that, but that is a true statement. Another thing that would count towards that, pizza toppings. What I mean by that is if I order a sausage, ham, and pepperoni, and they put pepperoni, ham, and sausage on my pizza, it's the same thing. For those of you who can't have sausage and pepperoni, change that with mushrooms and green pepper. Mushrooms, green pepper, and olives. If we put them on in a different order, does it change the pizza? Hopefully you all agree not. If you can really taste the difference, then you're weird. So there's a couple of examples of both of these. There are many, many more. I'm just blanking out on those at this current moment. So let's talk about how to find a permutation versus a combination. Let's take a permutation. A permutation is actually just using tation. There we go. I can spell kind of, unless it's the word principle. In which case I can spell. I just spelled the wrong one. Thank you, Emily. So a permutation is essentially the counting principle, but the idea is that we're not going to be replacing. So it's utilizing that non-replacement concept. It can be spelled out as this NPR, where N is the total number that exist, versus this R, which is going to represent how many we want. What I mean by that is, let's say we have a group of 16 racers, and I want to know how many ways can we have a top three. Well, clearly, if we have a top three, we're going to have, this would be written as a permutation as 16p3. What that means is we're going to take 16 factorial, and we're going to divide that by the 16 minus 3 factorial. Oh my gosh, I just realized I haven't talked about that, so let me stop right there and talk about that. So turn down your volume for a second, because I'm going to get loud. So this right here does not mean that this is 16 over 16 minus 3. You don't get to be excited about these. I know, you're not allowed to be excited. This is math. You're never supposed to be excited, unless you're a nerd. But you all are, so you should be. So all factorial means is if I say I've got 3 factorial, I multiply every number between 3 and 1 that exists, that are positive integers, and we multiply those. So 5 factorial is 5 times 4 times 3 times 2 times 1. 8 factorial is the same exact thing. 8 times 7, times 6 times 5 times 4 times 3 times 2 times 1. These numbers get stupidly large, stupidly fast. So in this problem, we would have 16 factorial over 13 factorial. If we did this, we would get 16 times 17, or 16 times 15 times 14 times continue on until we hit times 3 times 2 times 1 over 13 times 12 times 11 times a whole bunch of numbers until we hit 3 times 2 times 1. Now, if things are multiplying, those are all factors of each other. And in a fraction, the cool thing about factors is that they can cross off. So if I've got multiples, I've got 13 times 14, or 13 times 12 times 11 times 10 times 9 times 8 times 7. And here's 13 times 12 times 11 times 10 times 10. You'll notice that they match here. So the 13 would cancel out with the 13, the 12 with the 12, the 11 with the 11. And what we find out is these would all cancel each other out, and we would be left with 16 times 15 times 14, which is hopefully what you kind of realize the answer should be, because there are 16 people who can be first, 15 people who can be second, and 14 people who can be third if we were looking at this. I have no clue what that actual number is, so let's find out. There's a button for this, so I can do 16 times 15 16 times 14. Get that? I can also do this as a factorial. So one of the cool things we can do with our calculator is I can say alpha here, and I can do this cool thing here, and I can say 16, and there is a factorial button. We go to math right here, and we go to probability. Number 4, you'll notice, is a happy factorial. So I can say 16 factorial over, and because I don't want to make a mistake, I could say 16 minus 3, close the parenthesis, math, probability 4 factorial, and oh look, it's the same number. But there's something even cooler. I can go to math probability, and you'll see my NPR I was just talking about. That is the thing that will let me, oops, that's not what I want. When I do that, I want to make sure that I put in the number, so I need 16 math NPR 3, and it will just do it for me without having to really worry about it. Factorials are not, or permutations are not necessarily hard. They're fairly quick. You just have to ask yourself, does order matter? In the race situation, yes. If you're talking about ways to watch maybe specific movies and you tell me that order matters there, we can worry about that. So that's permutation. Fairly quick, fairly simple, nothing too bad, nothing too scary. So now let's talk about the combination. So the combination, also written in CR, where again, this is the number of things total, versus the number I want. This can also be rewritten as N over R like this, and this is going to be the typical way we're going to write that as we deal with these types of problems. And it does have a really screwy formula, and it's really gross, and I really don't want to use it, but we'll look at it anyways. So combinations are when things don't matter. So let's talk about a hand of cards. And I ask you, how many ways, or how many 5-card hands exist in a 52-card deck? Now, for those of you that do not agree with me, let me ask. Let's say I get a hand of cards. My first card is a 5 of clubs. I should really put that in black, but I'm not going to. My second card is going to be the ace of diamonds. My third card is going to be the 10 of hearts. Aw, it's a heart. And then when I color it in, it won't look like a heart anymore. Actually, that's a probably more realistic heart than anything else. I'm done making hearts. Let's say I get a 3 of diamonds. This is going to be a really crappy hand, folks. And I don't know. Let's get another 5 of spades. Pretty good spade. What do you think, Sean? Is that a pretty good spade? So that's the way that it's handed to you. Is this hand any different if I got the 3 of diamonds first? And then maybe I get the 5 of clubs, and I'm like, ooh. And then I get the 5 of spades. Sean made me sad, so now I'm not going to color in my spade. Versus the 10 of hearts. And then I get, what have I not included? Oh, I haven't included my ace of diamonds. Do these hands, are they different? What I'm hoping that you all agree with is that it's the same exact hand. It's a pair of 5s. You got an offsuit ace that's the same exact offsuit. The suits are the same. Everything's the same except for the fact that they were handed to me different. So if I were playing a game of poker, if I were playing 5-card stud, which is where I draw the 5 cards and then I make a bet and I do not get to redraw, that's just the hand that I'm stuck with, and I got to try to bluff people out, is this hand going to be any different? No, it doesn't matter how the cards get dealt. In fact, no one usually looks at the cards until after they're dealt. So that won't matter. So if we're doing this the hard way, this becomes 52 factorial. How many different things exist? Over, and we would do 52, and it's a 5-card hand. But then we're going to do something weird. We're going to multiply it by 5 factorial. and the denominator gets bigger. And that should make sense, because if I don't care how many cards I have, if I don't care about the order, then I want to eliminate all of those different orders for each of those things. Now that's really weird, and I don't want to have to memorize that. So we use our handy dandy calculator. Bam. Our handy dandy calculator, we could put 52, math. We go over to probability. On permutations, you may not use it, but number 3 you will definitely use a lot. NCR of 5, and bam. You get, apparently, there are 2,598,960 different types of poker hands that could exist. Just a couple of poker hands. The reason why the royal flush is so hard to get, because there are only 4 royal flushes that actually exist. The royal flush is the same exact suit with the jack, queen, king, ace, and the 10. Yeah, those are hard. So you got a 4 out of a lot chance of doing that. So that would be how you do it. Now, this is assuming you're using the yellow calculators that we have in class. If you have bought your own, you'll notice if you hit alpha and I believe it's window, this brings up this really cool menu here, and there will be a couple extras that are on the newer calculators that are not on ours. But 52 NCR5, that'll work. That works for any problem that's a combination. You just have to ask, does the order matter? All right, we're at 16. That's not terrible. So there's combinations and permutations. The only other thing I want to talk about, and this is one of my favorites, is the idea of rearranging letters. So let's say I have the word bat. How many different ways can I arrange the letters for bat? Well, we have bat. We can have bata. We can have apt or atub. We could have tab, or we can have taba. How on earth did we get those things? Well, if you look, essentially I'm saying that there are 3 possible first choices, 2 possible letters for the second. So if I pick the B first out of these, I have 3 different choices here. But then after I pick the B, there's only 2 choices. And then after I pick that, there's only 1 choice. So 3 times 2 times 1, just like counting principle, there are 6 possibilities. But what about the word KISS? KISS is one of my favorite acronyms. Stands for Keep It Simple, Stupid. Good stuff. Because if I rearrange KISS, what happens if I change the positions of the S's? Does that actually make a new word? Ooh, strange. I like how you're all staring at me still like, wow, this is really interesting, even though he's not talking to me. It's weird. So the question is, how do we deal with this situation like this? And this actually proves to be fairly straightforward. What we do is we say, well, how many letters exist? There are 4. So we would have a 4 factorial just like we'd expect. But for anything that's repeating, in the bottom we're going to put 2 factorial. And that is for each repeat letter divide by the, oh my goodness, number, why am I writing this, of repetitions. I guess because hopefully you're writing this. People are now just starting to write at the beginning of all of this. The number of repetitions for that letter. In this case, and this is kind of weird, but in this case I've got an S, so I've got 1 repeating letter that repeats 2 times.
Alex Rodriguez and Nathaniel Rodriguez. If you were in the building, your ride is waiting up front.
It would be 2 factorial. So that's 4 times 3 times 2 times 1 over 2 times 1. There's 12 ways to rearrange the words KISS. All right, somebody, give me a word that has some letters that repeat, that I can write on the board, that are not illegal for me to write on the board. Apple. I like apple, but it's only another 2. I need something with a lot of really annoying repeat letters. Mississippi. That's an annoying one. And what were you thinking? Difference. I'm trying to find a one that has 3 letters, like a letter that repeats 3 times. While you guys are thinking of that. Oh, there you go. I don't want to hear your lip, Aylin. Just because you're right and I was not thinking does not make you better than me. Actually, it does in this particular case. Congratulations. That was pretty desperate of you. Tom's asked for desperation. We'll do desperation next. You're going to have to probably help me. I've got to make sure I can spell that correctly. So, Mississippi, how many letters do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 factorial. That's a lot. Then I got to look and I have to say, do we have any repeat letters? So the first repeat letter I see is the letter I. How many times does the letter I show up? So this is 4 factorial. Times. What other letters repeat? S. S repeats 4 times. 4 factorial. Times any other repeat letters. P. That repeats how many times? 2. 2 factorial. And you type that into your calculator, which I closed. So I'm not doing that by hand. I'm not done. That would be crazy. So, yeah, someone is the calculator. Good job, Tom. You found your calculator. What you get? Don't do it by hand. Do the cool thing with the factorials. Good job. I knew I loved you. Totally platonically. Huh? Nothing. Don't ask questions. Meanwhile, I'm going to write the word desperation. Girl, I couldn't spell principal. Desperation or desperation? Despair. Yeah, you're a child. It's an E? You said desperation. Desperation? I can do desperation. Oh, wow, that's a really ridiculous number. 34,650 ways that we can write the word Mississippi. Desperation. How many letters do we have? So we got another 11 factorial. What is wrong with you all? Any repeating letters? E. E happens how many times? 2. Any other repeaters? Wow, really? That's it? Well, that's 11 down to 3. Have fun with that one. Okay, to amuse Emily, colloquial.
Give me that. Give it to me.
No,
You get another L in there.
Oh. Cool. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good job. That's why I teach math. 1, 2, 3. That's what? 3 factorial for the L's? What else do we have? O's? 2 factorials. I's is what? 2 factorials? You can start seeing this actually isn't a very hard question at all. Unless you can't spell. Hey, look. I'm curious. Who can spell onomatopoeia? Come on, that's a weird one. O. Okay. I was going to say, someone check it because onomatopoeia is a really... Did you get an answer for desperation? Okay, how desperate are we to come up with an answer? Just start reading the numbers. Oh, so there's only 19,958,400 ways to write the word desperation if we can rearrange the letters. 19,958,400. Colloquialism, 13 factorial over 3 factorial, 2 factorial, 2 factorial. Huh? Yeah, just start reading me numbers, man. Oh God, 25945. Ooh. 259,459,200 ways to write the word colloquialism. Or not ways, only ways that you can rearrange the letters. So there you go, folks. There's some random things. That's the type of stuff. The quiz will be on counting. It will be all of the counting principles. And we'll go from there. Have fun. Bye-bye.